Thank you everyone for coming. We're all set to go. Yeah. Thank you. Please enjoy. Yes.
Does anyone know how to turn this off? Oh, we need the computer to record, but don't want the projector. Perfect. Yeah, it's that's a good idea. We should zoom in. Nothing is visible from that distance. I don't think it'll be in the Zoom settings rather than the settings of the room. Hmm. Yes. Yeah. Oh, focus. There has to be a zoom option. We're just trying to figure out how to zoom that camera. That's weird. That's weird.
I mean, they've got OBS.
Okay,
They do in OBS.
sure. Yeah. And we can wait a bit since like Tom's not here
Yeah.
and till other people arrive. Oh, nice.
Why is that so small? Why? Why is this so small?
That's a good question.
Start video. Fail to start video. What is this? Rolling. No. No.
Interesting. Uh-huh. Huh. That's weird.
There we go.
Oh, yes, there we go. Perfect.
Okay, we're good.
Yeah. Okay. Right. Sorry for the wait. Just making sure we record this, and I guess let's get started. So first, I'll just introduce myself for a little bit. I'm Daniel. I'm a mathematical physics student here. I'm in my between second and third year. I was in the physics Olympiad back in Iran. In grade 11, then grade 12, became a physics Olympiad lecturer at the Institute for Physics Olympiad, Dr. Zamanpour's Physics Olympiad Institute. I teach mathematical physics, classical mechanics, analytical mechanics, electromagnetism. Um, then, yeah, right now I'm doing my bachelor's in mathematical physics. Second year, my interests are quantum gravity, differential topology, differential geometry. Um, yeah, um, mathematical physics as well. And yeah, that's about it. Any questions about that part? Okay. So, why classical field theory? So I presume most of you here are in physics or something adjacent to physics. Who here is in honors physics? Okay, three people. How about mathematical physics? Three people. Physics and astronomy? Two people. Applied math? No one. Pure math? One person. Okay. Okay. Who's here from engineering? One person. What about the rest of you? What programs are you from? Math. Oh, okay. Nice, nice. Any other majors here? Yeah.
We have a law major.
Oh, nice. Oh, nice. Very nice. So, which faculty are you under?
The arts.
Okay, nice. Very nice, very nice. So, in physics, a lot of our theories are field theories, right? When you start studying physics in university, you study classical mechanics, you study about point particles, right? But things aren't just points. You need to generalize it for continuums. So we assume things are everything here is a continuum and generalizes the same laws that we had for classical mechanics to something called classical field theory. Now, you might know that this university and most universities don't offer a classical field theory course. Actually, we do have one, but I believe it's a special topics course, so it's not offered regularly. Um, and who usually studies classical field theory? People who go to grad school for physics, when they want to pursue quantum field theory, because it would be a prerequisite to subjects such as quantum gravity, or what else? Quantum gravity for sure. If you want to study cosmology with a bit of QFT in it, that as well. Any type of theoretical physics that deals with quantum on an abstract level, you would need to study some quantum field theory. So, what are the prerequisites for quantum field theory? It's usually classical mechanics. In undergrad, you will have two classical mechanics courses. The first one, you would learn mostly about Newtonian mechanics. The second one about Lagrange and Hamiltonian formalisms of classical mechanics. And then you will learn a lot of quantum mechanics. You will take numerous courses on quantum mechanics. Then you'll learn quantum field theory. But the jump from classical mechanics union quantum mechanics to quantum field theory is a big jump. So the point of learning classical field theory, beyond the ones that I told you about, is to make that transition smoother. So this is mainly going to be aimed towards people who are in grad school who want to pursue quantum field theory, but they want a smoother transition. So about 2 weeks ago, I was looking at classical field theory textbooks, and I found this one. It's classical field theory by some author that I can't pronounce the name of, and I won't even try. I'll put a link on it in the Discord server if anyone's interested. I showed this textbook to one of the professors here who does quantum gravity. He was very impressed by the chapters. Can you guess how many chapters this book has? And it's not thick at all. It's like 200 something pages. Any guesses? Sorry? 13, okay. Up. Yeah. No, not even close. Very close. 46. This 200 something pages, I think it's 200 something, maybe 300 pages textbook has 46 chapters. So you can imagine how dense it is. So I read the preface. The author talks about, okay, this is mainly aimed towards people in grad school who want a smoother transition to quantum field theory, and they know classical field theory and quantum mechanics very well, but it said we won't deal with any quantum stuff in this book. Well, that was a lie. It has plenty of quantum stuff in this book, but that's not the main focus of it. And when we say classical field theory, we really mean classical and relativistic field theory. So just not quantum. Yeah. And what else? Yep. Started reading this textbook. It's really dense, the material of it. It jumps over everything. It's pretty much a review textbook. Um, so, and this seminar, we planned it very late in the term. Initially, we weren't even planning on having a seminar this term, but PhysClyb changed their minds during like the middle of this term. And I got this textbook around 2 weeks ago. And over the 2 weeks, I've been trying to bash my head against the wall and try to figure out what this author is saying, because it just doesn't go through any of the details and just jumps straight to the conclusions. And it has a lot of typos, this textbook. Like, I mean, a lot. And the thing with with typos is that it makes you skeptical of the text you're reading. So, and especially something as advanced as this and as condensed as this, you read something and you're like, am I stupid or this is just wrong? Sometimes mostly it's a typo, but sometimes you never know. You could be just not getting what it's saying. So hopefully they come up with a new addition to this textbook. This is a very new one. I think it was first published in 2019. So hopefully they'll make a better version of this. And it takes a lot from Landau and Lifshitz, a very famous series of books. One of the volumes is on classical field theory. So if you want a similar text that teaches you classical field theory, that one's a good reference. This one, I would only recommend this one if you probably have studied a lot of quantum and classical mechanics and are okay with not going through all the details. It's a very physicist-y textbook. The content, though, is amazing. The content of this textbook is fantastic. As I said, the prof I showed this to was very impressed by the content, but you don't learn it as in depth. Okay, so I think that's enough about talking about the textbook. Any questions so far? Okay. So this seminar was very rushed, as I said. Didn't have much time preparing for it, unfortunately. And if you guys were here for my previous seminars that I gave at PhysClyb, Those ones were way more fleshed out. The first one was on magnetohydrodynamics, MHD for short. It was mostly learning a lot of E&M. The second one was mostly learning about fluids, less equations, more heuristic stuff. We saw a bunch of videos about turbulence and viscosity at the end of it. And the third one was GRMHD, General Relativistic Magnetohydrodynamics. That one was mostly just GR. So here, I don't think anyone has taken GR. Has anyone taken GR? No. Okay. So great. Most of this stuff will be new. If you have taken GR, which no one here has, then some of this stuff will be a review for you. Now, I started writing the notes for this morning because I just didn't have enough time with the assignments and everything. I made notes for one chapter. In the table of contents, I mentioned that I'll be covering the first 6 chapters of this book, which include, I'll just read them for you what the content are. So, short review of classical mechanics is the first chapter. And when it says short review, it really means that. Symmetries, groups, Lie groups, Lie algebras, and representation theory. In SO3 and SU2, review of special relativity, Lorentz tensors, Lagrangian and the notion of fields, electromagnetism as a field theory. And the 6th one, I haven't even gotten to yet, so we won't be covering that. And I doubt if we'll cover the first 5 chapters of it, but we'll see. So, as I said, I only made notes for the first chapter. The other ones, I have to give the lecture off the textbook, which is not ideal at all. I like writing my own notes, especially because I can fix the typos. But unfortunately, as I said, just didn't have enough time. So, yeah, I guess that's that. If there aren't any questions, we'll get with the content now. Okay. So, I think this is too far to the left. I don't think people from that end can see here very well. Can you see here very well? Yeah? Okay. How about the people over there? Can you see that board very well? Okay. Okay. If you can't see anything, just tell me. I'll rewrite it. But so we'll start with chapter 1. I'll write big so everyone can see. 1. Review of classical mechanics. So first thing we'll note is that obviously speed of light is equal to 1 is equal to Planck's constant, right? Great way to start off a lecture. So here we just established that we're theorists. We don't care about these, but we'll mention them some places because it's good to see some dimensions somewhere. But this is the standard physicist theorist notion of doing theoretical physics. So this has a bunch of implications. This is that the dimension of mass is equal to the dimension of 1 over length is equal to the dimension of energy is equal to the dimension of 1 over time. Remember, this one is a unitless constant, and speed is length over time. H bar is units of action. So that's mass times velocity squared times time, and velocity is length over time. So this implies all of that. Second thing we'll know, this is the first thing. Second thing, our metric tensor is going to be the Minkowski metric, and it's going to be a diagonal of -1, 1, 1, 1, 1. So to all the particle physicists, I'm sorry if this offends you. Not really. This is the metric we pick. The other one is the +1, negative, negative, negative one. But this one is usually used in GR textbooks, so we'll pick this one. And also the Einstein's sum.
Explain what a metric is.
Yes.
People know what that is.
Yes.
Curious, is it twice contravariant as well? Why is the superscript for metric?
So you can always lower and raise indices with a metric. This is the inverse of the metric tensor, you know. And as Thomas said, I can assume that people here know what a metric is. The thing with this seminar is that I kind of have to assume you guys know a bit of geometry. I'll give an explanation for what a metric tensor is, don't worry. And also, we are using the notion of Einstein's index summation notation. There we go. Einstein sum. Okay, so what's the metric tensor? Ooh. Let's see. Let's see how much I want to get into the geometry. What's the maximum amount of time we have for this room?
7.
7, okay. Okay. Okay, I won't get too much into the details, but imagine if you have two vectors, you want a notion of distance, usually in physics. If you're not doing topology, you want a notion of distance. How do you get distance? Oh, by the way, is the microphone good? Like, okay. Because I want the recording to also pick up the audio. Okay. Yeah. You have two vectors and you want a notion of distance. How do you denote that? The mathematicians will say this is D, this is a metric, not a metric tensor, a metric of the vector V and V and W in some vector space V. This will give you the distance between these two vectors, which you can write as the well, in physics, usually these things become equivalent. The norm of these two, and usually in physics, it becomes the L2 norm. And this is the same as the inner product of V minus W with V minus W. For the mathematicians here, or mathematician, one person here, the mathematicians, they do the conjugate on this one, and they have a, what do you call this, a comma here. The physicist is the other way around. You conjugate this one, and you use Dirac notation. Okay, and this is equal to your metric tensor, a twice covariant tensor. We'll get into a little bit of what that means. It means that it transforms like a tensor. It takes in two vectors. So your vectors here are going to be V minus W and sure V minus W and itself again. And it returns a real number because it returns whatever the field of your vector space is over. Here it's going to be the real numbers. Okay. So this is what a metric tensor does. Usually all of these things become equivalent in physics. You have a metric tensor that tells you how to take the inner product, and that gives you a sense of norm, which gives you a notion of distance. So a concrete example here, I would say, imagine you have, actually, I'll leave it until the special relativity section to do the rest. I'll just leave this as this. So far, any questions? No? Okay. Now, so as I said, in classical mechanics, you have these laws that particles obey. Now we want to generalize whatever notion we had in classical mechanics for continuums. So one of the first things that you encounter is the notion of general coordinates. So you have some vector r, this is your position vector for some particle A. This is going to be equal to this. So your position is going to be a function of your generalized coordinates. And T for A being in this set. This just says from 1 to n, A can be 1 to n. This is just saying you have big N particles here. So one thing that you can note is that whatever dimension your space has, imagine we live in Euclidean R3, your each particle is going to have the dimension of your space times the amount of particles you have of degrees of freedom, assuming it's completely free, meaning no constraints. So what does that mean? The simplest case is 0 particles, but the simplest non-trivial case is 1 particle. If you have 1 particle in 3D Euclidean space, how many degrees of freedom can it have? 3. You can pick whatever coordinates you want. Let's pick Cartesian, X, Y, and Z. If you have, I'll get to your question in a second. If we have 2, again, no constraints, you'll have 3 for the first one and 3 for the second one, 6 in total. If they have a constraint, let's say you put a metal rod in between the 2 particles, that will be 5 instead of 3, because they can't, in spherical coordinates, if you describe them, the radius between them can't change.
You're not allowed.
You can rotate. So there's going to be 3 for the first one, X, Y, Z, and the second one, based on the first one, so the first one has 3 degrees of freedom, X, Y, and Z. The second one, described from the first one, is going to have a 2 angles, theta and phi, but the radius between them is going to be fixed. So that's how it'll get reduced to 5 degrees of freedom instead of 6, if they're constrained like this. So if we have constraints, it'll be less than 3n, 3 big N denoting how many particles we have. And if it's not constrained, it'll be equal to 3n. Question?
So you're basically representing the positions of many particles in 3 spaces, like the position of one sort of object in some really high dimensional space. Is that what you're doing basically?
Yep.
Okay.
So, okay, now, am I writing too big? Probably. That's fine. So we're going to define velocity to be, and I'm probably going very slow, which is actually a good thing because I don't know if I can properly teach the later chapters. So going to define it to be the time derivative of our position. My notation might be a bit bizarre for some of you. I'm going to just write down my notation clearly here. D mu is defined as dx mu. The x, sometimes I also write it as this because we're not only going to be dealing with x, but other fields as well. So it might be, so I might write it as dx mu. The pro about this notation, one of the pros, is that here Well, this is a contravariant tensor. Most of you might not know what that is. It's a coordinate. It has upper indices, right? But because of some geometry stuff, heuristically speaking, because it's in the denominator, it becomes a lower index. It acts like a covariant tensor. We'll get to that later. So that's why it's good to write it like this. One being that, the second one being because I'm lazy. And to be a good mathematician, you need to be lazy. So it reduces how much you need to write, which is always a good thing. And also, you will see that this is a lower index. So you won't be confused if it's a upper or lower index. It takes you less effort to see that, which less effort is always good in math. So, okay, we define velocity to be that. Okay, I wrote down that position is a function of those things over there. So using the chain rule, just like calculus 1 chain rule, or I guess calculus 3 multivariable chain rule, it'll be this expression. And remember, A just denotes which particle you're talking about. Doesn't really matter. You can omit those and it'll continue without loss of generality. Well, maybe some loss of generality, but that's fine. Did I do this right? No. No, why are my notes like that? That's what happens when you write your notes 2 hours before the lecture. So, okay, doesn't matter. Yes, yes, I'm describing velocity. Thank you. There we go. I do have it, just didn't see it. No. What? No.
Differentiate components.
Yes. Never mind the notes. Let's do it together. Doesn't matter. Okay. Taking the derivative of this with respect to that. Now I have to take the derivative of this with respect to t. There we go. Now it's right. Plus. Yeah. There we go. Okay. Great. Now we know how to describe velocity as with using our general coordinates. Perfect. Now we'll define the yeah, let's say define to make it easier. Our kinetic energy to be the sum of, this is just summing over all the particles. Because it's a scalar, you can easily sum all the individual kinetic energies of each one of the particles. Yep. We have this expression. So now, knowing this becomes a function of our q's, our general coordinates. Perfect. Any questions so far? How many of you have seen this before? Minority. Oh, okay. Oh, okay, more. Okay. Still minority, but okay. Okay. So, okay, maybe I'm not going too slow. If I'm going to, just tell me. If I'm going too slow or too fast, just tell me. I'm not sure what you have or haven't seen. So for a conservative force, who here knows vector calculus? Okay. Okay, I'm going to assume you know vector calculus. That's the bare minimum I'm going to assume that you know. Sorry if some of this is going to be alien for you, but I can't really assume all of you have seen geometry, but I'm going to assume you've seen vector calculus. If some vector field is conservative, let me. Better-ish. If a vector field F is conservative, what does it mean? Does anyone know what it means for a vector field to be conservative? Yeah.
That's the gradient of a scalar field.
Yes. Yes. So it means that the curl of this is zero vector, and it's not a function of time. So this implies that f can be written as the negative gradient. The negative is just convention of u. We call this the potential. Now, using our general coordinates, how low can you guys see? This is the lowest position it can go. Can you guys see here? Okay, so now we're going to write our f. The j just denotes the component, right, of our vector. It's going to be negative the gradient now with respect to our generalized coordinates of, let's call it v. The indices here talk about which component of your tensor you're talking about, or your object. We'll see what a tensor is later. Okay, so far so good. Let's define the Lagrangian to be, we're going to define it to be kinetic minus potential.
Daniel, what's
Yes.
V?
V, potential.
Oh, electric potential.
Any potential. Let's call it U. Doesn't matter. Yes. So force is actually a covariant tensor.
Those are like referring to different objects.
Right. So this isn't actually a vector.
Oh, okay.
I guess it's just incomplete notation.
That is
It doesn't show it there. You figure out that it's a covariant tensor by the gradient, because this is a one form. And again, I'm speaking geometry to most people who knows geometry here. No, I mean differential geometry, manifolds, covariant tensors, contravariant. Sorry? Yeah, sure.
Yeah, but I think it would,
Yeah.
in vector calculus, they,
Yes.
it's not a one. They refer to the gradient as a vector
Yes.
that you get, like,
Yeah.
they get a dot product.
Yeah. So, and that's wrong technically. It's it is a one form. For now, you can think of vectors as written in a basis. So vectors. Okay, let's talk some geometry then. When you talk about vectors, imagine there's some position in space. Let's say that point over there. This position is doesn't matter what coordinate system, what reference frame, whatever you choose to describe it. It's invariant under your descriptions. However you want to look at it, whatever bases you want to use, doesn't matter. Because this position is this position regardless of if I look at it this way or this way, if I tilt my head or not. Now, let's pick a basis. When we pick a basis, we can concretely represent the object that we're talking about. And we're going to get into some representation theory maybe later. Okay. And yeah, in a basis, if I pick a basis, I can represent my vector. Yeah, I think this is good because most of you haven't seen geometry. V can be written out as the sum of VI, EI, where E is the basis, and later this just becomes the partial derivative. For reasons that I don't want to make this whole thing a geometry lecture, so we'll say that. And one form is written like keep it like that. Sure, doesn't matter. I dxi. So for these bases, these are the components you get. And for these bases, these are the components you get for that. In linear algebra, you just straight go to the representation of them with column vectors and call it a day. That's not a vector. That's those are the components of the vectors. they change under what bases you use, what coordinate system you use. They're by themselves, they're useless. If you give me a bunch of numbers, I don't know what that describes. But if you give me the bases as well, I can sum them like this. Again, Einstein's summation index notation going on. I'm summing over the i's over however many cardinality of the dimension I have. If it's in 4 dimensions for special relativity, it's going to be 0, 1, 2, 3, 4. And so these are the invariant objects, and they transform differently. That we'll get into later. A force from this equation, you can see a force is a covariant tensor, yes.
Those who don't geometry, would it be a good idea to describe exactly what the Einstein convention is?
Sure. There you go. Now you know.
I mean, if you have VI, like 2 superscripts, you don't sum.
Oh, yeah.
3 subscripts.
Yeah, it only works for repeated indices, and remember, repeated indices have to come in pairs. It can be 3 or 4, and one has to be lower and one has to be upper. Yeah, those are the rules. And when you have repeated indices in that pair of lower and upper, you get a sum. Basically, you're just omitting the sigma here. And you're summing over the I in some index set I for the mathematicians. This is just saying what your set is that you're summing over. Usually for our purposes, it's going to be well, space-time, so it's going to be 0, 1, 2, 3, and yeah. Okay. Any more questions? Nice. So a Lagrangian is kinetic minus potential. If I plug this into something called the Euler-Lagrange equation, which is this, the total time derivative of the partial time derivative with respect to the velocity of the Lagrangian minus the gradient of the Lagrangian, it gives me 0. Okay, this is the Euler-Lagrange equation. A Lagrangian, most fundamentally, is defined as the solution to this equation. Whatever satisfies this, the Euler-Lagrange equations, that equation or equations, the I just means that you have that many components. It's a vector equation, you can think of it. A Lagrangian is whatever satisfies this. That's the fundamental definition of the Lagrangian, but we're not going to define it that way. We're going to define it as kinetic minus potential, what you usually see in physics courses. For a conservative force, and assuming that you can write your kinetic energy as only functions of your velocities, this goes both ways. So if you define a Lagrangian to satisfy this equation, from those 2 things, assuming those 2 things, you can derive that the Lagrangian is kinetic minus potential. But that's beyond the scope of this, so I'm just gonna, for making it easy, for the sake of making it easy, I'm just gonna define it as kinetic minus potential, and from that, you can plug it into here, you see that it satisfies the Euler-Lagrange equation. Yes?
That's circular reasoning, though.
Yes. Yes, the more fundamental one we're not going to get into. You define it as it satisfies the Euler-Lagrange equation, then you go on from there, but that's harder. So we're just not going to do that. I'm going to take the easier route. I'm going to define it as this. If I define it as this, you plug it in here, you see it satisfies it and everything is good. Life is good. Okay, so what does the Euler-Lagrange equations do? Well, I'm going to make a very heuristic, write a heuristic map here, very heuristic, very physicistic, but in the language of math. So imagine your Euler-Lagrange equations are something. I'm going to say it very vaguely because I just made this up, this diagram myself. They've taken your Lagrangian and spit out equations of motion. So the input is a Lagrangian, and the output are equations of motion. So Newton's laws, your Lorentz force and E and M, all of these are like equations of motion. And this is kind of the definition of the equations of motion. So you'll see a lot of people in your physics degree that call things equations of motion that aren't actually equations of motion. Equation of motion, and this, I guess I'm just being pedantic here. It doesn't really matter. But for someone who likes to be rigorous, an equation of motion is defined as whatever you get from inputting your Lagrangian, and whatever it spits out, that's the equations of motion. That's the definition of equations of motion. Now, how do you know you have the correct Lagrangian? Well, you define the Lagrangian as this. But in the more fundamental way that I talked about, if you define this to be your Lagrangian, how do you know you have the correct Lagrangian? Well, the correct Lagrangian is the Lagrangian that gives you the correct equations of motion. And this is how the book Taylor defines it. And it's actually very true. So the Lagrangian, again, recap, the Lagrangian is whatever satisfies the Euler-Lagrange equation. We know what the Euler-Lagrange equation is. And the correct Lagrangian is the one that spits out the correct equations of motion after you plug it into the Euler-Lagrange equations. Now, which ones are the correct equations of motion? It's whatever experimentally you've verified. Yeah. So you can postulate equations of motion, verify them experimentally. And note, an important thing in physics is that you prove postulates. So a lot of people use the terms axioms and postulates interchangeably. The thing with that is, it all depends on how you define things. But if we want to pick a good definition, in my opinion, is that postulates are your guesses in physics. Now, they can be guesses based on intuition, pattern recognition, human intuition, whatever. You guess that these are the laws, and you experimentally verify them. You prove them. Well, more rigorously, I should say prove. Because if, why not? Let's talk a little about philosophy. Very little. If you know about David Hume, you know he mentioned the problem with what's it called? The word for it, the mathematical proof of there we go. Induction. There's a problem with induction in physics that if you say, okay, here's my law, I'm gonna experimentally verify it, like Newton's law of gravity. If I drop this piece of chalk and it broke, my bad. I'll get you a new one. I'll get you a new one. Sorry.
I have one more. You need it.
No, I'm good. But I have more Hogoromo. I have Hogoromo at home. So
We have the book at 6:30. 6:30. Yeah, and usually I wouldn't care, but I'm the first speaker, so I kind of need this time.
I see.
So if you could wrap stuff up, that'd be great.
Okay. That's very unfortunate. I thought we had it till 7, no?
We have to yell
Whose fault is this? Okay, so
There's a room in the physics building. I know it's far, but
Yeah,
it's usually-
3:13, yeah.
That's not a one. That's not a one.
well, no, not that. On the second floor, there's this room with the chalkboard. Like you did your seminar there on magneto hydrodynamics.
oh, that was
That's like that. It might be a bit of smaller chalk, but
Like this study.
I don't know if people want to walk that far. Let's. I guarantee you, we're gonna go there. At 7, they're gonna kick us out. Okay, let's pack up because these guys booked the place. Sorry for this. I don't know whose fault this is. Probably. We're gonna yell at someone at some point, but
I think no, like more personalization.
like an hour at least. I can go more, but an hour at least because
If you could probably like
sure.
yeah.
I'm gonna get you set up. I've got to leave like before 7. So
Sure.
I'll just set it up on
Yep.
this.
Yeah.
And then you can go to like 2 videos. All right.
Sure.
Okay.
That's fine. That's fine.
Yeah, my goal is
We greatly apologize for all of this. This is not in our attentions at all. And hopefully tomorrow's seminar will go much different. There's one tomorrow.
Yeah.
By a very cool grad student on their research on, what's it called? Theoretical systems with black holes.
What room are we going to now?
Which room did you say?
4061.
4061.
Yeah.
We are going to 4061, please.